Good afternoon to all. So my talk will be much less mathematical than what you had today, I guess. It will deal with something I started to work a few months ago. So I started with a master's student, and it has to do with everything which is trying to capture the context in the process of the generation of a sequence. So why context is important? Basically, there are many situations where you would like to capture context. So when it comes to non-sequences, you have, for example, the user in web search. And when it comes to sequences, then you have plenty of different examples, like the speaker and spoken language recognition, topic and style and document generation, user in web browsing, and user activity in music listening, etc., etc. So the context is important to capture because if you are able to represent it correctly, then you can use it to compute other quantities that you would like to compute. For example, if you can represent correctly a user just by looking at the behavior the user has when searching on the web engine, then you can use this information eventually to predict better search results. Okay, so that's one of the motivations of capturing context. And then why distributed representation? Sorry, skip this slide. So distributed representation is a hot topic in machine learning. I guess many of you know this. It's very connected to deep learning. So everything which has to do with learning how to represent objects. And it is interesting because of many different things from a practical perspective. So the first one is that it is able to capture geometrically. So there is a notion of distance between objects. Different types of objects, whether it is users, images, text, etc. Okay? So this has been used quite successfully, for example, in image where the error recognition rate has been divided into by the introduction of techniques based on deep learning and implicitly on representation learning. And the other thing which is of interest also is that that kind of models of distributed represented based models are able to leverage different sources of information. So, for example, if you want to compute information which is related to images and text with distributed representation, you project images and text within a vector space or within a space in general with a metric, and then you can use the notion of proximity of images and text to benefit from one source of information or the other. Or to take another example, if you have user behavior on a web search engine, you can look at this user also clicking on any web page and try to leverage all this information and to project the user still in one representation space that you can use for other tasks at hand. So this is the main motivation for distributed models. So in this talk I will mainly discuss the two aspects, so how to capture context and how it has been captured, well, just presenting a few words. And then I will discuss how distributed models have been used for generated building model that generates sequences. And I will also focus on both aspects at the same time, that is, how distributed representation have been used to build models for generating the sequences. So basically, the problem is that you can roughly try to estimate the probability distribution given a data set. Okay, so this gives you a cost estimation of a density. And then what you will try to do is to learn for a different data set, which is usually much smaller, this same kind of probability distribution, but trying to take into account the fact that you've observed a bigger data set comprising a lot of different observations, which might encompass the same context or other context. Okay? So the goal is to, well, as I said, to leverage this in order to do some tasks better, where you can use the representation that has been learned. So taking into account context can be seen in many different settings. So basically, I categorize them into 3 different categories. So the first one are when you want to, well, when you represent the context as explicit factors in a probabilistic model, so using, for instance, latent variables. And then when you try to define families of parameters, where you define a subspace of the parameter space that will represent all the context, and then you relearn the parameters for a given context and you project back to the family. So that's another way to leverage the global information you have on all the sequences and still to be able to learn something which is related to a given context. And the third one is, well, basically given a prior on parameters which depends on the parameters you've learned on the full dataset. So the first one is when you use probabilistic model to capture context. So to give an example in text, you have the latent Dirichlet allocation, which was a paper written by Blake and Jordan in 2003. So basically, which says that word generation is governed by a generative process, which is first you select a distribution of a topic following a Dirichlet law, and then you choose a topic with a multinomial whose parameters depend on what you've drawn from the Dirichlet, and then you select a word within the vocabulary which follows the multinomial which is parameterized by the topic you've selected. Okay? And then the context will be basically the problem of computing the probability distribution over the topics, that is over theta. So a second way to capture context is to use also mixture of probability distribution, where you will basically try to learn a mixture over all your data sets, all the sequences you can have at hand, and then you will try to estimate for a given subset of the data set, that is the contextual data set, the probability, the posterior probability of a mixture component being observed. And an instance of this kind of technique, which are based on mixture, is the work of Omondro in 1995, where basically what he proposed was to learn subspaces of the parameter space. So if he started with very simple model, which is basically one simple model, which is just the parameters you've learned by maximum likelihood, and then whatever the parameters you project back to those parameters. So basically it's a constant solution, no context. And then you can learn a set of separate models and try to project back the solution you've learned onto one of the solutions and try to select the closest one and say this will represent the parameter of my generative process given the context given by the contextual data set. And then he defined, well, 2 other methods, and the last one is quite interesting because he basically defined what is no-code and auto-occluder. So basically what you do is that you learn to project from your parameter space onto a space, a representation space of your parameters, and then to project back. And within the projection, what you try to learn is to project so that if you have a random noise around your parameter, you'll still project back to the same point in order to capture the regularities. And then the third category of models that try to capture context are based on the idea that you will define a kind of prior over your parameter. So what you do is basically estimate your parameter theta over a full data set, and then you will say that the parameter that will be learned for a specific context, that is for a specific set of observations related to one object, will be close to the solution that you found previously. Okay. So this has been used, for example, for gestural recognition with hidden markup models. So this was the work of Wilson and Bobbitt in 1999. Basically, what they try to model is a movement of the hands, okay, so a gesture, and each state of the AT, the QT, correspond to one specific position within the gesture movement. And this state generates a distribution which is a normal centered around a mean mu of j and a given covariance matrix. And what they do is that they say that for a given context, for a given user, you will have a theta parameter that will be learned for this specific sequence. And this parameter will modify the mean of the Gaussian, explaining the position in space of the hand. Okay? And they do this by using a linear transformation of theta to modify the mean mu. And this has been extended, for example, by parameterizing also the variance, the covariance matrix of the Gaussian and the work of Redden and Arthur. Related to this idea of prior over parameters is the idea of regularization, where you still want to stay close to the solution you found on the full dataset. So basically what you do is that you learn your model given a given cost function, so you find the best parameters, theta star. And then in the contextualization part, what you will do is that you will add a cost that will depend on your parameters you found on the full dataset. Okay. An example of this instance of models is one which was used to adapt a search engine to a given user. So basically, you train a neural network on a set of labeled instances, where the instances are pairs of document, query, and relevance assessment, saying whether the document is relevant or not. You learn this model, and then if you have specific information about a user, about the relevance of some document or some queries he or she made, then you can use this information in order to modify the model. And the way it is done is basically by using a truncated gradient, which is in a L1 regularization, where what you do is when you have the derivative with respect to a given parameter of the model, you will keep it to 0 if it's below a given threshold. So basically what you say is that if the derivative with respect of the cost with respect to one parameter is too small, you just don't change the solution you found. Okay? So now I will discuss a bit the problem of representation learning and sequences. So as I said, it corresponds to the idea of projecting a given point, given object from an original representation space of the object, which is the raw data, to a given multiple. This is related, the idea of what we should do this is related to the manifold assumption, which was stated in the RIFI and NL paper, and which basically says that if you know something about the distribution of the data, then it gives you some clue about the classification task you are trying to achieve. And the second one is that real-world data concentrates on two small part of manifolds, and then there is nothing out of them. And the third point, which is quite important, which is related to the classification task, is that when you have points which are close together in the representation space, then they should share the property of having the same class in average. I said this can be used to represent many different complex objects. For example, nodes in a graph. So I'm working on this kind of projection. So how to leverage the information about the connection between nodes in a graph in order to represent them. And then in sequences, in that case, it's mostly about representing the state, which is akin to the state of each element, but here we are within a continuous space, so the state is within a vector space. And of course, the context. So this object also will be represented as a vector in a vector space. To give you some example of how this is used in sequence generation, so I say 3 of them. The first one is done in LIP6, the lab I'm from, by mainly Ludovic Denoyou, so who is working on this and reinforcement learning. Here the idea is to predict the traffic. So you have different streets and intersection between streets, and each intersection corresponds to one latent variable in a represented space, so within a vector space. And for each representation you can predict the traffic, so this is a regression problem here. So the function f of theta of representation of an intersection at a given time t will be used to predict the traffic at this time, at the time t, and you have a const function which is related to this. Then you have a second thing, which is the dynamic process, which is basically trying to predict the next state in the representation space given as a function, of the previous state. So this is h gamma of zi here. And the third component of the cost function, which is used to learn all the zi's and the theta and the gammas here, which are the parameters of h. So the third part of this cost function is related to the geographical similarity, proximity. So basically, Eij will be equal to 1 if the two intersections are directly connected, and to 0 otherwise. Okay? So this gives a regularization with respect to the fact that the two intersections are close together. And then when you want to learn this, so it would be in a transitive framework. You will optimize this over all the observation, and then you can use the function h gamma in order to predict the next state for a given street intersection, and then predict the traffic at different time steps. Okay? So this is one way of doing this. Another example is for handwriting sequences. So this is a work of Graves in 2013. And basically what it is to say that you can model the position of a pencil. So when you sample at given regular time intervals, as a mixture of Gaussians, where the parameter of the Gaussian, so it's a bidimensional Gaussian, you have two variance parameters and one mean, is represented in a vector space. So the state is still here within a represented space, and you use this representation, this state S here, to predict the next y. Okay, and this y is used to predict the different components that you need in order to compute your normals. So basically the means and the variances and the mixture coefficient here. Okay, so it's basically a linear function, and then you have some housekeeping in order to have the sum of the dice sum to 1, etc. Okay? So that's you have a proper quality distribution. And the last example is more closely related to what I'm doing. So it's a neural network language model, which uses two different kind of representations. So there is one for the state, which represents the context, the previous words, and you have other representation, one for each word of the vocabulary. And what you will do here is first, if you want to predict the next word to appear in the sequence, you will use a lookup table, which basically gives you one vector for each word of the vocabulary. Then you will compute the state, so depending on which setting you are in, whether it's a recursive function of the state or whether you are in a convolution network, you will compute the state, which depends on the representation of the words and maybe on the previous state. And this will be used in order to compute the distribution probability of our words in your language model. So basically, well, usually it's roughly something which is proportional to the exponential of the dot product of the vector BW and the state. BW is again something which is dependent on the word you're considering. Sorry. So now I will talk about dealing with both aspects, the distributed representation and the sequence. And I will give you first an example of how Graves, because I just gave you the example before, used, built a notion of context for generating sequences of converting signal, and then I will present what I'm doing now. So what he's done, so it's exactly the model you had, so basically where the position of the pencil is given as a mixture of Gaussians. And then what he did is basically use a priming sequence. So the priming sequence is the first one in the two examples that are on the top of the slide. And this sequence is used in order to set the state ST, which is the last state which generated the final E, for example here, they are. Okay? And then, starting from this, he used the generative model he's learned in order to generate the sequences which are just below. Okay? So this is one way to build context for a given sequence, is to give it some past observation and then start from a state which is biased by what you observed before. Another work which was done in 2014 with, from Le and Nikolov was based on the idea also of representing the context as a vector. So here it's a neural network language model, a very simple one. You have the cat stat, which are the three previous words, which are associated each to one vector, and then you have something which represents the context, here a paragraph, but it could be a document, for example, and you will use this, well, here in their model very simply by just averaging the vectors and using this in order to predict the next word in the sequence. So basically, in that paper of model that I'm working on, so it's based on the Le and Nikolov approach, I started by, well, first trying the model as it is, and then trying to play a bit with that kind of idea. And so roughly the problem setting is the following. You have a family of functions, which are all the functions that correspond to your generative process. So basically the search space, the parameter search space, of the parameter space of the model. And then what you try to do is represent the context and have a function phi that will modify this function in order to produce a new function, a generative function, which will explain the generation of any sequence for a given context, for example, a given user. And one important property of such function is that there exists a neutral element, so that you can first learn the general generative process and then try to learn the parameters for the context at hand. Okay, so the problems are basically what kind of function phi we can use, and of course having a balance between complexity and generalization, because if you have a function phi which is too complex, then you won't generalize to a new example for a given context, especially because you have a very small sample for say, a given user. In the work I've done is based on is applied to information retrieval, which is basically a setting where you have a set of documents. So this is actual examples. It's the first one I found by looking at the first corpus, which is track 1. So there was no selection actually. And so you have a set of documents, a query, and the goal is to rank the relevant document before the non-relevant ones. And the measure is just minimum average precision, which is basically sum of all the ranks where you found the relevant documents of the precision, that is the number of relevant documents you found so far divided by the rank you are at. Okay. And to solve that task with contextual distributed models, what I did is basically use the language model hypothesis, which says that if a document is relevant for a query, document D1 is more relevant for a query than a document D2, then the probability of generating the query given the language model of the document D1 will be greater than the probability of generating the same query for the language model of which corresponds to D2. Okay? So the basic model information retrieval is the unigram model, which is basically each word is, given, which says basically that each word is independent, so the probability of generating a sequence is just the probability, the product of the probabilities of generating each word, and estimated by maximum likelihood. This gives just a ratio of frequencies plots. How much time do we have? 5 minutes? Okay. So the limits of this model is basically that dependencies are not taken into account, of course, because you don't consider context at all. So you lose the information, especially for bigrams, trigrams, or more complex term dependencies. And there is a problem of probability mismatch. And it has been shown with neural network language models that both issues can be tackled with neural networks, because using the distributed representation, you leverage the information about a word for other words. Okay, so the proximity between the representation of two words means something, and then you can capture longer dependencies by using convolution networks or neural networks or recurrent neural networks, for instance. Okay. So I started with this. The setting is just a convolutional setting, where I have a first function file, sorry for the dash, that computes a state vector given the n previous words before the word I want to predict. And then there is a document which is represented by a vector, and then there is a function psi that just combines the state vector, which is just obtained by the context, and the document vector. So this is basically if the psi function is just a sum of the two components, this is Le and Nicolas work, and then you can use different things. And we started with simple things, which are component-wise product of the terms of the vectors. And the procedure for learning this is quite standard, so we start with word embeddings which are generated using word2vec, so it's a fast and cheap way to get the vectors. Then we train the neural network model, language model, by trying to work with a gradient descent, which is trying to maximize likelihood. And then for each new document that we have, that we want for which we want to predict the relevance of to a query, or basically the probability of generating the query, we compute the vector, and then we have a score which is a linear combination between the generation probability given by the neural network and something which is the unigram distribution. This was used just as it is done in information retrieval, because the neural network probably loses some information because it uses a small vector as a context, and this reduced representation in IR usually leave out the noise, which is problematic for information retrieval because you deal with very specific words. So if you have let's say Obama in a query, you don't want any president of the United States to be an answer for this query. Okay. So this is what we observed in practice. So we varied lambda and we computed the mean average precision. And this is the baseline. Well, the first model that we used VM25, which is a classic model in information retrieval. This is another language model. And what we observe, well, we were quite concerned about this, is that for a very small value of lambda, which says basically that the neural network language model is almost not used, we have the best results. So we then looked at the actual probabilities that were given to each term of the query to see whether the result did make sense or not. And what we observed is that, as I said before, the problem was mostly with very specific terms. Okay, so you won't distinguish between documents talking about any instance of a given entity, because what your neural network will predict that is that it can generate any kind of animal, for example, instead of having a specific animal. So we started to look at different transformations that we'll just unmonitor, which are translation transformation. And the basic idea is to translate vectors to go from general concept to more specific concepts. So an example is given just here. So what we want to do is that when the neural network state is, for example, on animal here, which corresponds to the general neural network model, what we want is to move this state to bring it back to something which is closer to what the document is really discussing, which is, for example, type. So we model this as a transformation, which is the identity to preserve the state, and then which is modified by a small rank linear transformation. Okay. And well, the preliminary experiment have shown very good results, and well, I experimented with other transformation, but this one was so far one of the simplest and one of the best results. So I will just end. Okay, thank you.